bounded by y equal root x and y equal x over 2. And again, finding the intersection points, sometimes it's easier just to guess and check. 0, 0, and what is this one? Well, if you plug in 1 into both, do you get the same thing? No, what about 2? What about 3? What about 4? Ding! Right? Square root of 4 is 2, 4 over 2 is 2, 4 over 2.
It didn't work on the test, which is hard.
It should have. Okay, we're not mentioning the test now because the person watching the video didn't take the test yet. Okay, so we know how to compute this area, right? We just go top minus bottom from 0 to 4 and do an integral. But now we're going to do a three-dimensional solid. So what if I told you this is the base of a solid? Think of a paperweight. The paperweight has a base, right? Every time I remove a cross section from here, so there's all of these cross sections like this. If I remove a cross section and look at it, you know what it's going to be? It's going to be a square. So they are going to tell you what the cross section is. Okay, can you imagine what the shape looks like? Every time I take a slice up, whether it's here, like if I take it out over there, you're going to see a square, except it's going to be a smaller square. But you take it from the middle, then it's a bigger square, and then if you take a slice over here, then the square is going to be smaller. But no matter what, whenever you slice it, the cross section will be a square. Can you imagine what that thing looks like?
I've caught a loy.
A what?
I've caught a loy.
That's what the
I know, but it's like it's like
An alloy plant?
yeah, like a little cross section of an alloy. That's what it's gonna look like. No?
Maybe. But I don't think the cross section would be squares though.
What is it?
Like this though?
It's like an oval.
Yeah, it would be more ovalish, yeah?
Oh, never
Hey,
mind.
why isn't the thing coming on? Did they plug it back in? Where's the thing? Oh, they didn't plug it back in. Boo. No wonder.
It's like a little Pokemon DS game, and then you stack them up.
Oh, I see what you're saying. It's gonna be like okay, never mind. Cause us square is not rectangle.
Okay, the thing's still not coming on. What do we do? Did you guys do GeoGebra?
No.
What?
GeoGebra, the
No.
app for geometry.
No.
What is that?
Well, GeoGebra is good for calculus as well. All right, finally. Okay, so you see the gray plane? The gray plane is the XY axis. Wait, I'm gonna turn the camera for Lee. Lee, this is for you. Hope you can see that. Okay, so the gray plane is the XY plane, and do you see we take a slice perpendicular to the x-axis? See how it's a square there? So they can make different shapes here. So this slider, so see how the cross section, like over here, the square is small, then it gets bigger. That's because the distance between the two curves is bigger. And then as you get toward the end, look, the cross section gets smaller again. But every time, no matter what, it's a square. That's a pretty good view, yeah? So what would happen if you add up all of these pieces? So this, see like right here, if you make one square, break it up into 7 squares, 14 squares, 27 squares, and of course, what we're gonna do with the integral is add up an infinite number of squares. Well, it only goes to 100, but you can kind of see, that's what it kind of looks like. What does that look like? Like a slug. Yeah, it's kind of like a slug. Yeah? But then, what if the cross section is something else? You know what I mean? Like, what if the cross
Yeah.
No, that's a slug.
No,
They're all slugs.
that's the slug. That's the real slug.
This is the real slug.
They're all slugs. But see, what happens is the cross-section shape doesn't change. I only want one. See? It just gets bigger. The diameter is bigger, then it gets smaller, depending on the distance between the two curves. And then integral, we'll add them all up. Boop, you get a slug. No, this one is more like a croissant, yeah?
No, that's a slug.
Okay, whatever.
The other one was just like a triangle.
Well, the main thing, you don't really need to know what the shape looks like. You just have to be able to compute the volume. So how do we do this? Well, you basically gotta know geometry.
Oh no.
Oh no.
What do you mean, oh no? Okay, so the first part of the homework, all you have to do is write an integral that represents the volume. And then in the later problems, then you gotta actually compute those integrals. So let's write an integral that represents the volume, where a cross-sectional slice perpendicular to the x-axis will be a square. So you know what you should do? Draw a square. Now, to figure out the area of the square, okay, thank you. I forgot to do that. To get the area of a square, don't you need to know the side?
Yeah.
But the side is the length of the rectangle, isn't it? Right, remember from the picture? So the square is just coming up like this. So what is the length of this rectangle right here? Come on, we've just been doing it. You did it on the last test. Top minus bottom. And then if you draw the rectangle horizontally, then it's gonna be right minus left. But in this case, we drew it vertical because the equations were given as y equals, right? That's a big hint. So top minus bottom. Root x minus x over 2. Now, if you know the side of a square, can you figure out its area? Yeah. It's just the side squared. That's the area of the square. It's just that the side of the square changes as you go throughout this region. But this thing has a thickness, right? Because it's not really a square. A square doesn't have a thickness. So this is like a basically, what do you call this shape here? It's like what's a square with a thickness? What looks like this?
A slab.
So I said a Pokemon.
A tile.
Yeah, a Pokemon card. A Pokemon card. Anyway, and what is this thickness? Since I drew the rectangle vertically,
Yeah.
it's dx. Because remember when you draw your rectangle, this is a change in x, right? But when it's infinitesimally small, it's dx. And then when you draw the rectangle this way, this is a change in y, but when you make it infinitesimally small, it's dy. So that's why now, some of you have not been drawing in your rectangles. You really need to draw in the rectangle to see what's going on. So this is the volume of this Pokemon card. And if I want to get the volume of this entire thing, what do? We add up all of these Pokemon cards from 0 to 4. Since you're doing the integral in terms of x, you go from the x coordinate here to the x coordinate there. It's that simple. So we're not doing anything different, right? We're just adding up an infinite number of things, or just adding up a different thing. Okay, now what if the cross section was an equilateral triangle? There's certain ones that come up on the AP exam. So again, they're all slugs, right? So here's an equilateral triangle. What is the base of this equilateral triangle? Well, the base is lying right on that rectangle right there, because it's coming up like this, right? What is the length of the rectangle? Top minus bottom. There you go. And if you know the side of an equilateral triangle, can you figure out its area? Yes, we learned the formula for that in geometry.
We did.
Yes, and I also, like if you were in my SAT class, or if you looked at the cheat sheet for the SAT and you put the formula down there, does anybody remember it?
No.
It's like 3 root 4.
Root 3 over
4.
4 times the side squared. So here, this is really useful in calculus. The area of an equilateral triangle is root 3 over 4 times the side squared. Now, what happens if you can't remember that? Then you gotta go on the side and go, okay, let's see, if I know the side, how am I gonna figure out the area? I guess I gotta go 1/2 base times height. If you think of this as the base, then wouldn't this be the height right here? Now, how do I figure out that height? Well, this is a 30, 60, 90 triangle, right? Because it's equilateral. And if this is S, then half of it would be S over 2. And in a 30, 60, 90 triangle, if you know the short leg, how do you get the longer leg? You multiply it by root 3. So that would be the height. But then isn't that the same thing as root 3 over 4 times S squared? Yeah, it's just better to memorize it. Just memorize it already. So, what is the side of this particular equilateral triangle? Top minus bottom. But that's just the area. There's a thickness to it. What is this thickness? Dx. Why? Because I drew the rectangle vertically. Anytime you draw the rectangle vertically, it's going to be dx. You draw the rectangle horizontally, it's going to be dy. So this will be the volume of this triangular slice. If I want to find the volume of this whole slug, you add up all of these slices from 0 to 4. And how come we go 0 to 4 and not 0 to 2? Because it's dx. Anytime you do an integral in terms of x, you go from the x coordinate here to the x coordinate there. All right, another shape that you're going to see is the semicircle. That's why they have those three on here. These are the three most common shapes on the AP exam right here. Okay, so here is a semicircle with the diameter lying right on this rectangle here. See, it's coming up like, this is like a kamaboku. You guys know what that is, the fish cake thing? Okay, so this, what is the length of the rectangle? Top minus bottom. That's the diameter of this semicircle. Now, if you know the diameter of a semicircle, can you figure out its area? Yeah, easy. A semicircle is half a circle, so 1/2 pi times the radius squared. Now, if this is the diameter, wouldn't the radius be half of that? Yeah, so you just go diameter divided by 2 is the radius. So pi r squared is a full circle, but this is just a semicircle, so 1/2 pi r squared. But it has a thickness. And what is this thickness? Dx. How come it's dx? Because I drew the rectangle vertically. And then all I have to do now, add up all of these slices from 0 to 4. Okay, these are the three most common ones you're going to see, but once in a while they throw in some other ones, like isosceles right triangle. But then there's two ways to do it. What if they said the isosceles right triangle has the leg lying on this rectangle here? The leg is in the xy plane. Well, what is the length of this rectangle? Top minus bottom. So, top minus bottom. Now, if you know the leg of an isosceles right triangle, can you figure out its area?
Sure.
Yeah, this one's easy. Just go 1/2 base times height, right? Because isn't the base and the height the same if it's an isosceles? You know what isosceles means, right? These two legs are equal. So just go 1/2, let's move it a little bit more. 1/2 base times the height, but the height is the same as the base, so that's squared then, right? Isosceles right triangle means the two legs are equal. But it has a thickness. And what is that thickness? Dx. And you simply add up all of these slices from 0 to 4. Mr. Park, they're all 0 to 4. That's because we're doing it in terms of x. It's going to go 0 to 4. And what about the other? I'll squeeze it in over here for the video. What if the isosceles right triangle was like this? Oh, that's an ugly one. This way, where the hypotenuse is lying on the xy plane. So know the hypotenuse of a right isosceles right triangle? Can you figure out its area? Yeah, this is all geometry, right? Computing areas of shapes. So how do you want to do it? There's lots of ways. Okay, here's one way. In a 45, 45, 90 triangle, if you know the hypotenuse, how do you get the leg? Divided by root 2, right? So this one will be the same. And then you can just go 1/2 base times height, right? If you think of this as the base, wouldn't this be the height? Yeah. Okay, so you just go 1/2 base times height. Since they're both the same, you just square it, but it has a thickness. And what is that thickness? It's dx again. And then if you want to get the volume of this whole thing, you just add up all of these slices from 0 to 4. Now another way to think of this is, hey, Mr. Park, isn't this triangle simply half of a square? If you draw the square like this, right? And what's the side of the square? Isn't this the side of the square? So you can go 1/2 of this square. That's what that is. You get the same thing. It's just a different way of thinking about it. And of course, now tonight, like I told you, the first part of the problem, of the problems, you're going to have to just write the integral. You don't have to compute it. But then later on, then you're going to have to compute it. So, Mr. Park, I will have to compute 5 separate integrals? No. Can you see that if you just compute one of them, you can get all the rest? Like, for example, if I compute this integral, you know all the rest, or you don't have to, like, reinvent the wheel. What you talking about? Okay, let's just compute this one first, okay? Wait, I want to see if I can I go to the left a little more? What does it look like? I'll just erase some. Okay, I'll do it up here. Let's compute this integral here. So how do I do this integral? What do I need to do? You need to multiply it out. Okay, that's the only way you can do it. Don't even think of u substitution. Okay, so if I multiply this out, you're going to get this squared, x, minus 2ab. What is 2 times this times this? The 2's cancel out, so don't you get x root x? Wouldn't there be x to the 3/2 then? Plus this squared. 1/4 x squared. Come on, this is algebra 1, people. Not even algebra 2. A minus b squared is a squared minus 2ab plus b squared. Okay, that's easy. X to the nth, that's the easiest antiderivatives we can do, right? So what's the first one? 1/2 x squared, easy. Minus, make the power 1 bigger, put the reciprocal in the front, make the power 1 bigger, put a 1/3 in the front, that'll make it 1/12. Don't gotta go from 0 to 4. Okay, plug in the top number. 16 over 2. Minus 4 to the 5/2. Square root it, then raise it to the 5th power. That would be 32 times 2/5. 64 fifths plus 64 over 12. You can reduce that by 4. 16 thirds. And then of course minus 0 plus 0, right? So everything else is 0. And then to simplify this, you simply need to make the least common denominator of 15. So that's going to be 120 minus multiplied by 3, 192. Multiplied by 5, that's 80. So that's 200 minus 192 over 15 for a final answer of 8/15. So the volume of this slug, the one with the cross sections that are squares, is 8/15. Now once you compute this one, all the rest, like this one, isn't this the same thing as taking the root 3/4 and throwing it outside like an unwanted pet? Yeah. Because look, this integral is the same as this, except we got a root 3/4 on the outside. So all you have to do is take this answer and multiply it by root 3/4. What about this one? Okay, be careful now. Now, if I know this integral is 8/15, what do I need to multiply by to get this one? Pi over 8. Because this 1/2 gets squared, and so that's 1/4 times 1/2, you get 1/8, right? Be careful if you're going to do this, you got to do it right. What about this one? If I know that one is 8/15, what is this one going to be? What do I need to multiply by? 1/2. And what about this one? Be careful. 1/4. That's why when you get the problem of the same type, you got the same region, you don't need to reinvent the wheel. Because otherwise, you really want to do this for all 5 problems? Yeah, I don't think so. Okay, now, what about if they say cross sections perpendicular to the y-axis? Which they will. So let's erase this. So now, cross sections perpendicular to the y-axis, that means the slices are this way. Which means what? What do you have to do when you draw the rectangle horizontally? You gotta change the equations to x equals, yeah? So this becomes x equals 2y, and this becomes x equals y squared. Okay, so let's just do the square. So cross sections perpendicular to the y-axis are square. So it's going this way now. So draw the square. What is the side of the square? Right minus left, because you drew the rectangle horizontally. So right minus left. And if you know the side of a square, how do you compute its area? You square it. That's why they call it a square. So that would be the area of each cross-sectional square, but it has a thickness. What is this thickness? Is it dx or dy? It's dy because we drew it horizontally. And now I'm going to add up all of these square slices from 0 to 2. How come 0 to 2? Because we're doing it with respect to y. You go from the y coordinate here to the y coordinate there. And that integral is going to be pretty easy because you don't even get fractional exponents now, right? When you square that. Okay, so these are the most common shapes, but once in a while, they'll throw in something there just to see if you can handle it. Like I've seen this several times on the AP exam. They say, okay, cross sections perpendicular to the y-axis are rectangles where the height is 3 times the base. I think you can handle that. Well, what is the base? The base is lying on that rectangle right there, and then it's coming out like this. See? Like that. Well, what is the length of the rectangle? Right minus left. So you go right minus left. And this is the base. If the height is 3 times the base, what would the height be then? If it's 3 times, just go 3 times 2y minus y squared. Can we figure out the area of this rectangle? Yeah, just base times height. So just go base times height. So wouldn't that be this then? But then it has a thickness, which is dy. And then I'm going to add up all of these things from. You guys haven't learned yet when the ringing ends, that's when you say the limits. You add up all of these rectangles from. You gotta wait till the song finishes. Let's try it again. There you go. We finally caught on. So all we're doing is adding up an infinite number of slices to get the entire volume. And that's what calculus does. You add up an infinite number of little things to get the whole thing. Isn't that pretty neat? Understandable, right? And then of course the next next challenge is once you write the integral, you gotta compute it. Because you're gonna get some that has, trig, u substitution, integration by parts, the normal procedure. And then, after we take the next test, you're gonna have a test where every single one, you're gonna have to use your graphing calculator. Most students like that one, the average of that one is sky high, you know why? You don't have to know any antiderivatives,
Yeah.
right? Because you just use your calculator. But then of course, then the intersection points are gonna be like
Crazy.
not nice numbers, right? But then you use your calculator. Alright. Okay, so the only other thing we gotta do today, go over the test. Yep. Okay, wait, let me turn this off.
Thanks, I can.
Yeah, go ahead.